Hello, this is Aditya, and I am teaching a lesson on electron configuration for the Intro to High School Chemistry class. So, what is electron configuration? First, we're going to look at an atom of sodium. Sodium has 11 electrons total, so the first shell would hold 2 electrons, the second shell would hold 8 electrons, and the outermost shell would hold only 1 electron. I would advise you to open up this link. Just search a periodic table on Google and open this link. It should be the first thing you see. It has very helpful properties for each element on the periodic table. So they always have, electrons always have the same structure where they fill in electrons from the innermost shell. So Na will fill its inner shell with the 2 electrons first, then the 8, then the 1 left over will go in the outermost shell. Now, the whole point of electron configuration is to organize these electrons into boxes. These boxes will be called orbitals, but the boxes are just a way of representing them. So we're going to learn about the box method. Here, we see that we have different letters for boxes. So we have an S box, which will hold 2 electrons. Okay, so the S box is one box, and each box holds 2 electrons. The p orbital has 3 boxes. It will hold 6 electrons. The d orbital has 5 boxes, so it will hold 10 electrons. And the f orbital has 7 boxes, so it would hold 14 electrons. We have 4 different types of orbitals that are assigned to the letters S, P, D, and F. These orbitals, it'll make more sense why they exist later on. So each box will hold up to 2 electrons. Yeah, so it's no guarantee that each box will hold exactly 2 electrons. Sometimes it can hold 1, and sometimes it can hold 0. So now we're going to use the box method with sodium, Na. If you look to the right of the slide, you're going to see an order in which arrows are going through all these different orbitals. So 1s is the first orbital you would work with. This concept is a little bit abstract, so if you have questions, just ask me during class. Don't worry about that. 1s is your first orbital, so the first orbital that Na would fill with its first 2 electrons is the 1s orbital here. And when you fill these orbitals, you fill them with upspin electrons and then downspin electrons. So each box, if it's completely filled, should have 1 upspin electron and 1 downspin electron. And then, so that's 2 electrons filled up. Sodium still has 9 more. So you go to the next arrow, 2s. So 2s is another s orbital. So it only has 1 box, which means it fills another 2 electrons. This means that it will have an upspin electron and a downspin electron. So that's 4 filled up. Sodium still has 7 more. Now we start here again. The next orbital we come up with is 2p. So 2p is a p orbital, and as we saw on the last slide, p orbitals have 3 boxes and can fill 6 electrons. So you would fill them like this. That's 6 more electrons filled, 3 with the upspin and 3 with the downspin. Well, I'll explain how specifically you have to fill this later. And then that's 10 electrons total, and you have 1 electron left, so you go to the next orbital, 3s. 3s is an s orbital, so it has 1 box, and you'd only put an upspin electron because that's all the electrons that sodium has. So I want you to go through these and try to figure out the electron configuration as best as you can. If you need to, you can rewind in the video and see these arrows I put here. You have the elements hydrogen and neon and phosphorus. So I'm assuming you've had the chance to pause the video and work these out. So we're going to look at these now. So hydrogen has only 1 electron, so you would start from the 1s orbital, and you'd fill 1 electron there, and then you're done. So the way you'd represent that is by writing 1s1, and actually you would write it as an exponent. That's what it looks like here. So when you fill 2 electrons in the 1s orbital, you would write it as 1s2. And 2 is the max number you can have for an s orbital. 2s2 Once again, this 2 at the top here represents the amount of electrons you can fill. 2p6, the 6 represents the maximum amount of electrons you can fill in the p orbital, and then 3s1 just shows that you put 1 electron in the 3s orbital. And if you add these exponents up, in this case they're not really exponents, but if you add these exponents up, 2 plus 2 plus 6 plus 1, you will always get the number of electrons in the element, because this adds up to 11, and sodium has 11 electrons. So hydrogen would be represented as 1s1. So this should actually be 1s, and then 1 is an exponent, but that's not really a big deal. So you can see that like this number here, all these numbers here would add up to 1, because there's only 1. And then for neon, we see that the first orbital is 1s. It fills up both the electrons here. It still has 8 left. It fills up the it would fill up the 2s orbital, so that would be another 2 electrons, and then it would still have 6 electrons left, right? So the 2p orbital, you would need the 2p orbital, which holds 6 electrons, and so that would hold the last 6 that neon needs. So the way you would write that is 1s2, because it fills the whole 1s orbital with all 2 electrons, 2s2, because it fills the whole 2s orbital with all 2 electrons, and 2p6, which would fill the entire 2p orbital with all 6 electrons. And so phosphorus is a little bit more difficult, but it's still easy. So phosphorus, you would start from 1s again, obviously. 1s, it would fill 2 electrons, so that's 1s2. And then 2 more electrons, 2s2. 6 more electrons, 2p6. And then you keep going here. The next one you have is 3s2. And then you would not fill this entire 3p orbital, right? Because you have 1s2, 2s2, 2p6, 3s2, and then you start here, 3p1, 2, 3, and then you already have phosphorus. So phosphorus would not actually fill the entire 3p orbital. It would only fill 3 electrons. So the way we would write that is 1s2, 2s2, 2p6, 3s2, 3p3, because it only puts 3 electrons in the 3p orbital. So now we're going to learn about noble gas notation. If you haven't noticed, as the elements get bigger, the electron configuration gets a lot longer. And at times it can become very, very tedious to say the whole thing, starting from like 1s2, 2s2, 2p6, 3s2, 3p6, and all that. So the noble gas notation was invented for people to be able to shorten it down. So if we look at phosphorus's electron configuration again, 1s2, 2s2, 2p6, 3s2, and 3p3. It's a pretty long electron configuration. It can be a little bit annoying to say like the entire thing. So for the noble gas notation, we're going to look at which noble gas has the most electrons but still has less than that of phosphorus. So I'm going to go back to the previous slide. Phosphorus is here, so this is element number 15, and they're asking you which noble gas, so the elements on the right side of the periodic table, so all of these guys, which element on the right side of the periodic table has the greatest amount of electrons but still less than that of phosphorus. And that would be neon. So neon has the most electrons of any noble gas that still has less electrons than phosphorus, because the only noble gases that have less electrons than phosphorus are helium and neon has more electrons. So back here, we say that which noble gas has the most electrons but still less than that of phosphorus, we'd say neon. And so the way of properly writing this is essentially you just skip this entire 1s2, 2s2, 2p6 part. So when if we're going to look back here, 1s2, 2s2, 2p6 is the electron configuration of neon. So instead of writing 1s2, 2s2, 2p6 in phosphorus's electron configuration, we can skip all that and just write neon like with a bracket Ne, close bracket, 3s2 and 3p3. So we'll see that here. We're going to look through and then find the electron configuration of the following elements: magnesium, calcium, bromine, and arsenic. So these are all pretty big elements. all of them are really, really big. So we have the key here. It's a lot easier to just use the noble gas notation and shorten it as much as you can. So for magnesium, normally you'd have to write 1s2, 2s2, 2p6, 3s2, but you can shorten that and put neon next to it because neon has the largest noble gas that comes before magnesium in the periodic table. And calcium, instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, you can just shorten the whole first part out and then substitute it with argon because argon is a noble gas with the most electrons that comes before calcium, and then just write 4s2. So the same thing goes for bromine, except for bromine, actually not bromine, for these transition metals, there are some different properties that you will have to know, but that's something that's a little bit more advanced and we might learn it later. But sometimes the electron configuration won't fill up the orbitals in the way that it does that I've just showed you. But that is how you would use noble gas notation.